Hey guys, welcome to Digital Srini channel on YouTube, and I hope you have subscribed to this channel. If not, this would be a great time to do that. In the last video, I talked about semi-supervised GAN, and in fact, we went through a little bit of an in-depth explanation, so I definitely recommend you to watch it. And if you haven't watched that video, well, you should definitely watch it. But here is a short explanation. SGANs or semi-supervised GANs can be used if you have the benefit of humongous data set, but then only a few images are labeled. Now, if you only have few images labeled, if you follow regular convolutional neural networks, the accuracy that you get is not as high as what you would get with our semi-supervised GANs. And this has been published, and we talk about this in our previous video. So in this video, let's go ahead and implement this in keras. Again, this is going to be very similar to a regular GAN, except for the discriminator part. Again, our discriminator, we are going to divide that into a supervised and unsupervised type of discriminator. But again, let's hope that we would see better accuracy with a semi-supervised GAN approach compared to a convolutional neural network approach. Again, if you haven't watched my previous video, you are probably wondering why I'm talking about classification in the context of GAN. Well, that's because you're probably thinking about a GAN as something that you use to generate new fake images that look realistic. That is true in typical GANs, where you're saving the generator, a trained generator, to generate new images. In this case, we throw away our generator. We don't care about our generator. We are using the generator only to make our discriminator better. That too, the supervised part of the discriminator better, which is nothing but a classifier. Okay, so without any delay, with that short introduction, let's go ahead and jump into the code. And let's start by looking at our standard MNIST classification implementation, which I have done in the previous video. So without any explanation, or without much explanation, I guess I can't stop from explaining things, but without a lot of explanation, let's go ahead and run this piece of code. So what this is doing is, let's go ahead and import the libraries, because that may take a time. We freshly started this session. So I'm importing my keras libraries there, and then I have a function that actually pre-processes my images, loads MNIST dataset, and then divides each image by 255. So this is our way of scaling the pixel values. And the next set of this function actually gives me about 96 images out of the entire 60,000 images, because the whole point of this video is to make sure we understand how our SGAN approach gives us much better accuracy compared to our standard convolutional neural network approach. For that, we need to understand how the standard convolutional neural network behaves, or what type of accuracy we can expect. Okay, so let's define our data set. Let's get our X and Y, and let's not even look at those. Let's divide our XY to our X train and Y train. And here, if you see, I have about 96 images for training and 24 images for testing. So this is a small data set. And let us define our model. And in this model, I'm defining a conv 2D with 32, conv 2D with 64 filters, conv 2D with 128 filters. And I'm using ReLU activation here. And in GANs, the discriminator part, we are using leaky ReLU. I could have changed this to leaky ReLU. You can do that and test how the result looks like. The reason I'm comparing this with our GAN, let's jump to the GAN. I'll come back to this point later, but right there, when I define my discriminator, I'm doing exactly the same. conv 2D 32, 64, 128, except with instead of ReLU, I'm using leaky ReLU. That's it. And then flatten and drop out 40%. And now I have my output with how many ever classes we have. How many classes do we have? 10 classes, right? So that's the output. And then when I define my supervised discriminator, which is a classifier, I just take this and add softmax activation and sparse categorical cross entropy as my loss function and compile this. Now let's jump back to my MNIST classification. So here, 32, 64, 128, flatten 40%, dense with 10 outputs, activation softmax, loss function sparse categorical, optimizer atom. This is almost identical except for this activation function. So let's go ahead and define this model. And while it's defining, so now we can go ahead and train the model. Normally I wouldn't train it while doing this because it takes time, but this is such a small data set. This training should be done within 30 seconds, if at all. And let's look at our accuracy. You see our training accuracy is 100%, but our testing accuracy is 75%. And for the testing, we have 24 images. On those 24 images, it's doing 75% accuracy. What type of accuracy does it give me if I have all 10,000 testing images from the data set? We'll see that in a second. But let's go ahead and save this model. And if you're curious, you can go ahead and plot the training curves. And this is my standard way of doing things. And the reason I'm showing here is you see how this is kind of saturated at about 75%, and I'm not getting any better. You can try different models by adding different layers and everything and see if you can make this any better, but at some point you're limited by the total amount of training data. Okay, so let us apply this to all of our 10,000 testing images, right? Because our testing data as part of your MNIST data set is 10,000. So if I confirm that, yeah, 10,000 images. Let's apply this model on all of our 10,000 images and print out the accuracy. So this gives us what the best accuracy is on all these images. In fact, that's not bad, 76.8%. So let's see with our GAN approach, if we are going to get any better than 76.8%. I hope we'll get at least 10% better accuracy, but let's see. And the prediction, yeah, let's go ahead and plot our confusion matrix. So all of this, so we can come back and then compare after we do our GAN. Okay, so there you go. Now the moment that most of you probably tuned into. I'm going to share these files with you. So I added a whole bunch of text just in case you want to go through the reasons, what is semi-supervised GAN and all that. You can go through that, and I have a link to the paper that you can go through. But let's not clear anything. Let's not especially clear the plots, but we can clear the variables. Yeah, let's start from scratch. Okay, let me import all the required libraries. Again, there is not much. In fact, I'm not even using the categorical because initially I thought of converting my data to categorical. I'm like, why do that if I have sparse categorical and loss function? Okay, so I am defining a generator here. I showed this in the last video. This is very similar to a generator that you would use in a regular GAN. So you start with the latent dimension. In our case, we'll do 100, and you add a dense layer with enough nodes that can be reshaped into the output image that we are looking for. So we start with these many nodes, and then we slowly we reshape that, and we do a con 2D transpose with leaky ReLU, these many filters, size 3x3, stride 2x2, and then this gives you 14x14 image, and then next one 14x14. Finally you get 28x28. Go ahead and plot it out if you really want. So let us define these, and this is again our regular GAN, so I'm not explaining a lot. In fact, I added a couple of lines here so we can test out. Okay, let's say my generator is defined generator with a size of 100. Let's go ahead and print the summary. This is a better way of visualizing what's going on, right? So we have a vector of 100, and then we define a dense layer of 256 by 7 by 7, which apparently is 12,544. And we are gradually reshaping that from 7 by 7 to 14 by 14 to 28 by 28, because this is the image, output image that we want that goes into the discriminator, correct? Now, let us comment these lines. We don't need that. And now let's define the base discriminator, which is basically a feature extractor. I could have called this feature extractor, but that confuses a little bit. So let's leave that as defined discriminator. Again, if you watched my previous tutorial, you know that we have broken this down into three parts. One, we are defining a discriminator that ends by giving you a dense layer as the output. And then we define a supervised discriminator by adding softmax to this. Okay, and then we'll get to unsupervised in a minute, but this is how we divided this. So let us define our discriminator. I just showed you this. This is very similar to what we have done with our MNIST classification right here. So what we have done, it takes in an input image of 28 by 28 by 1. 32 column 2D, 64, 128, flatten, drop out 40%, and final dense layer is with 10 classes in this example. So let us go ahead and define that. I'm not even going to print it because we just saw how that structure looks like. Now let's define the supervised discriminator. Again, we have two discriminators, right? The supervised discriminator is nothing but a multi-class classifier, which means we need a softmax activation. You're going to get 10 outputs, so you have to do argmax at the end of it, but the activation is softmax. And then the last we are going to use is sparse categorical cross entropy. Not just categorical cross entropy, because our input data is integer encoded and not hot encoded. Okay, so this is it. Again, there is not much to explain here. This is a standard classifier, as standard as it gets. Now, when it comes to unsupervised, we just need to take this, which is nothing but your supervised, but up to the before your softmax activation, right? So that's exactly what you have done here. Again, I added all the explanation. We are only following the process that we got from this paper, where they talk about adding a custom activation function to the unsupervised discriminator, which is of the kind zx or zx plus 1. Okay, so first of all, let's define the custom activation. We saw this in our last tutorial. This is basically, what is our zx? Summation of e to the x. So that is nothing but summation of e to the x is your zx, and your d is nothing but zx or zx plus 1. That's exactly what we define here. So this function returns or dx right there. I need to add this function as a additional layer as part of our model, and in keras sequential, it's very easy. You have a lambda layer that you can use to add your own custom function layers. So that's exactly how we are going to define our unsupervised discriminator, which is the standard discriminator in a GAN. Exactly a standard discriminator, except there we use a sigmoid activation function. Here we are using a lambda or custom activation layer. That's it, instead of sigmoid. So let us go ahead and define this. And now comes the GAN part. This is the combined model of generator and the discriminator. Which discriminator? The unsupervised discriminator, right? Which is nothing but a binary classifier. Standard GAN. So that's this part does not care about supervised at all. So let's go ahead and run this. And again, the inputs are your generator and your discriminator. And we are going to set our discriminator as non-trainable, like our regular GAN. Which discriminator? Again, the unsupervised. Always think of unsupervised as the one that you always had. Supervised is the one that came in as a new one in this approach. Okay, so we did this part done, and the next set of functions are just a helper functions. Hey, when I call you, just give me real samples. When I call you, give me like 100 points from some images from our MNIST data set or something of that sort. So let's go through these one by one. So first of all, load real samples. I could have renamed this function as pre-process images. That's exactly what this is. In fact, if I go back here, the previous code that we looked at, this is exactly what the same function, get images ready. Except here, I used divided my x by 255 to normalize them. And here I'm just doing x minus 127 or 127.5. Why? Because in our generator, this is important, because in our generator, if I can find it, custom activation, where is my generator right there. We are using tan h activation, which goes from -1 to 1. So let's go ahead and make all the values -1 to 1. So that's how I want to normalize that. So that's exactly what we are doing right there. So this is fetching a bunch of images, all the images from my MNIST data set, and normalizing them and returning it. That's it. So this basically helps us get the data ready. And the next set, select supervised samples. This is exactly the same function as this one, select subset of images. So this is, we're calling it supervised samples because we want to discriminate between supervised and unsupervised samples. So here, this gives me how many ever supervised samples are, let's stick with 100 because that's the experiment we have done there. So this returns me a array of 100 images and corresponding labels. And we are also ensuring that the data is balanced by getting 10 images for each class. Okay, that way the data is nicely balanced, and it's fetching random images. Okay, that is done. Now, generate real samples. We always had this in our GAN, right? So whatever GAN we talked about, we always had this function called generate real samples. It is going to give us basically real images. In fact, I should call this fetch real samples, because we're not generating them. We are actually looking at our data set. We're looking at our images, and then we are randomly picking a subset of those real samples, and then we are adding a label called ones to all of our real images. Again, in a GAN, when you're supplying your images, real images and fake images to the discriminator, we tag a label of 1 to the real images and 0 to the fake images. This is exactly that one we are talking about. This is where some confusion may come from, because there are two types of labels here. This is Y is the first type of label, and this other label right there is the second type of label. This label corresponds to the label 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you are looking at some other data set, this is the cats and the dog and monkey and all of these, elephants and so on. That is this label. The Y right there is basically telling us that, hey, this is a real image and not a fake image. That's what this Y is. So when I call this generate real samples function, it gives me a bunch of images, corresponding labels, and another label, which is nothing but all ones. That's what this gives me. Similarly, I have generate fake samples, which gives me fake samples. But to generate fake samples using our generator, we first need to generate latent points, right? Or latent vector, or noise vector if you want to call that. That gives me how many ever, like if I say give me 10 of those, so it gives me that many latent vectors. So let's go ahead and define this function that gives us latent vectors, and then let's define a function that gives us fake samples, which takes in the generator model as input, and you use your generator.predict on to your latent points to give us the fake images. And for the fake images, our label is 0. And for fake images, we don't have real labels because we're just generating fake images. So there is no label here. So when you call the generate fake samples function, it's going to return only two things, a fake image and a label of 0. So let's go ahead and run that function, and we are slowly getting there. And summarize the performance. So we're going to call this function at the end of certain number of epochs or certain number of steps. So what does that do? It basically gives me a plot, and we are saving that plot as PNG. And a plot of what? A plot of all of these generated images right there. Yeah. And generate fake samples right there, right? We are generating the fake samples. It just gives me a plot of fake samples, which tells me how good my generator is doing. But more importantly, it gives me the discriminator accuracy. So remember the supervised discriminator that we are going to train, we want to evaluate it. And this is exactly what we are doing. Yeah. So you have your data set where you get your real Y, and you're going to evaluate this. And we are going to print out the discriminator accuracy periodically. And we are also going to save our generator model and that supervised discriminator model after every so many epochs. Why am I saving generator model? Just because I'm curious how my generator is behaving. So I'm going to save the generator. Normally, you just discard it. You don't care about it. And I'm saving the supervised discriminator, not the unsupervised. You don't care about unsupervised discriminator anymore. It's useless at this point. This is why we are doing this entire approach. This is it. That .h5 file is the reason I'm doing this whole process. And some print screens for to output the status on as it's training. So right there. And now comes the final training part. We went through this again. I showed snippets of this in the last tutorial, but again, pretty much the same thing. You are selecting some supervised samples, which is basically you get 100 images, right? Because that's our number of samples we want. So you get 100 images and corresponding labels. And now you have your batch per epoch and number of steps calculated. So now come down to the meat of this function, which is for each of these steps, go ahead and do the following. The first thing you would like to do is train, let me create more room here, is to train the supervised discriminator, which is the classifier that we really would like to take home at the end of this training. So how do you train the supervised discriminator? You actually need to get real samples for that. So here, this is your discriminator supervised that we are training on real samples right there. X supervised real and Y supervised real. Okay, and these samples are extracted from our X supervised and Y supervised, which is nothing but our 100 images. So out of our 100 images, it's actually fetching a batch of those images and supplying that to our supervised discriminator, and then we are training it. The weights are updated here. That's it. That part is done. Now we go to the next part. What is the next part? Well, you have your unsupervised discriminator. And how do we typically train our unsupervised discriminator? We first train it on real images, fake images. Next. That's exactly what we are doing. We are going to get real images with real label. This real label is 1, right? And we don't care about the label that is associated with that image. That label only makes sense when you're training the supervised. I really want you to understand this part. The way we wrote this function, what are we doing here? Generate real samples. When you go back and generate real samples, it's returning us 3 things. It's returning us the image, the corresponding label. If the image is 5, the corresponding label is 5, right? In our MNIST dataset. And it's also returning Y, which equals to 1 for real samples. Generate real samples gives you 3 things. Now, of those 3, when we train our supervised discriminator, we train it on image corresponding real label, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We do not care about whether it is a real image or fake image, because for supervised training, it is a real image. We know that. So that is not part of the training. When it comes to training your unsupervised, we don't care about actual label. Is it 0, 1, 2, 3, 4, 5? We only care about, is it a real label or a fake label? Y real is 1. That's the key difference here. That's it. And then we are going to train this right there. And once it's trained on the real, now we have to train it on fake. So that's what we're doing down here. So now the discriminator is trained. Once that's done, you train your generator. How do you do that? Using the combined GAN model, where we fix this unsupervised training as untrainable, non-trainable, and then only train the generator. So we are generating the latent points right there. And then your GAN model, you're training it on these data points right here. The generator weights get updated. We had a print statement, so we see something on the screen, and we call the summarized performance. In this case, this often right there, meaning like after every one, go ahead and summarize this performance, and we are going to see these on the screen as we are training. That's it. And once you have that, let's run these. I don't think we did. Where did we stop? Let's go ahead and run all of these. I'm not sure if we did that. Up to the train part. Yeah, right there. And now comes actual calling these functions. So first of all, I define my latent dimension as 100, and we have to define the discriminator. I'm assigning that to a variable called disc. And supervised discriminator, I'm assigning that to a variable called disc supervised. Unsupervised discriminator, so we have 3 different things. So that's what I'm adding here. And this disc, I am just providing as input to these 2. Okay. And my generator model, obviously calling the function define generator, and we have to define the GAN model. This is the combined model that takes in the generator and the discriminator, right? So that's why we have generator right there, unsupervised discriminator. Now let's go ahead and get the data set, which is basically load our real samples. There you go. And we have 60,000 by 28 by 28 by 1 and 60,000 labels, corresponding labels. So we have our data set ready. Now 60,000, and if we train it for 10 epochs, that means divided by 10, every let's see, what is our batch size? Sorry for doing this. Again, this is where my lack of preparedness. What is my batch size? My batch size is 100. So let's go down, and we have 10, and we have 60,000. So I'm just trying to calculate how many steps it's going to take, and based on that math, every 600 steps, if I'm not wrong, it's going to save the model and generate the save the PNG file. So yeah, I think I did the math right there, and let's go ahead and start this run so you can see exactly what you would expect to see on the screen. This is the one that's important, the C, which is the unsupervised model loss. And as you see, it's going down. That's a good sign. Eventually, we hope that goes down to 0.00 something. Let me go ahead and stop this because I have done this for 10 epochs already and saved the model. Excuse me. So let's load that saved model. And for 10 epochs, this is the model that got saved. So let's go ahead and load it. And now let's do the same exercise that we have done earlier here in terms of calculating the accuracy and printing out the confusion matrix. So for that, let's go ahead and load the entire 10,000 images and pre-process them. And now let us go ahead and print the accuracy. Hopefully this is better than 75 or 76% that we got before. So there you go, 93.8% in our 10 epochs. And this didn't take that long. It took like probably 10 minutes or so on my system. That's got 16 GB of GPU. That's tremendous increase. If you forgot, did we save them as a different model? Let's see, let's start from here. There you go. 76.8%, the standard convolutional neural network approach. Very similar model, except I embedded that into a GAN. And here we are getting 93.8%. So that's a significant amount of improvement. So you can get much better training on limited training data set. But then the requirement here is you need to have a lot more images that you can use for feature extraction. If you only have 100 images, you're not going to get this type of accuracy. We are getting this type of accuracy because we are using all those images, the 60,000 minus 100 images, or including these 100, all those 60,000 images for feature extraction, and only using our 100 images for labeling purposes, for multiclass label purposes. And if you're curious about how this looks like in terms of our confusion matrix, let's go ahead and look at the confusion matrix. Here it is from our GAN approach, and here it is from before. Yeah, obviously a lot more right there. Errors, and here we are doing a much better job. Now, if you wonder about generator, hey, is the generator also usable? Yes, of course it is usable. I'm going to load my generator model and plot. And there you go. That's a pretty good generator, as you can see. They look very realistic handwritten digits. Okay, so this again turned out to be as expected, almost a half an hour long video. That's exactly why I have broken the explanation and the implementation part into two separate videos. I hope you really learned something from here and from these two videos. Go ahead and hit the like button if you really like this type of content. Let's meet in the next video with a different topic. Thank you, guys.